Okay, thank you for the introduction, Pavel. So I'm Wonyo. I'm a graduate student at Stanford, but currently taking a leave to do some kind of alternative military service in Korea. So anyhow, I'm going to talk about some verification problem for the math.h implementation. So this is a joint work with Rahul and Alex. And this talk is based on the two papers presented at PLDI and POPL. Okay, so let's get started. Okay, so to describe the problem that we want to solve, let's consider the log function and its floating point implementation as shown in the slide. And this is a floating point implementation because it uses floating point operations such as subtraction and multiplication colored by blue. But as you know that floating point numbers have a fixed number of bits always, but the log value, the exact mathematically exact value of log usually have infinite number of bits. So this indicates that any floating point implementation cannot compute the mathematically exact result for most inputs. In other words, there must be some kind of a precision loss for any floating point implementations. And you're particularly interested in finding a tight bound on the precision loss of those floating point implementations. So this is a problem that we are interested in. And formally speaking, suppose that you're given a mathematical specification F and its floating point implementation P, and also we're given an input interval X. Then our goal is to find a small quantity theta automatically that bounds some kind of error between F and P for all inputs in the capital X. So in other words, you'd like to prove a bound and the maximum precision loss of the floating point implementation. Okay, this is a problem that we want to solve. And at least the problem statement looks quite simple, right? But as we solved this problem, we found that solving this problem is not that easy. And in this talk, I will mainly focus on the challenges, the two main challenges that we encountered when we solved this problem. And the first challenge that we encountered is that those kind of floating point implementations, especially industry standard implementations of math.h, such as Intel's implementation, usually use floating point operations as well as bit level operations and intermix those two types of operations. So what I mean by bit level operations are those operations that directly manipulate the value of each or some parts of bits, such as bit shift operation like PSLLQ in the slide, or bit shuffle operation like PShuffD in the code. Then some of you might wonder that how can we actually use those kind of bit level operations in a meaningful way in floating point computation. And to explain that, let's recall the definition of floating point numbers. I think most of you are familiar with the definition. And the important point is that the parts of the 64-bit of a floating point number is partitioned into three regions. And each part always represents some numbers to a part of the floating point representation. Like most significant 12 bits are assigned to sign and exponent bits and so on. And by using this fact, you can actually use those bit level operations in floating point computation. And this is a favorite example to show, my favorite example to showing that kind of intermixes. So suppose that we are given an integer n and would like to compute 2 to the n in double precision number. Then a naive way to solve this problem is to do a bit shift to 1 by n to obtain 2 to the n in integer. and do the conversion operation to get the double precision number 2 to the n. However, this approach has two main problems. First one is that the conversion operation is computationally expensive, and more importantly, this approach works only for a small range of inputs. And actually, there is a more efficient and scalable way to solve this problem. And uh, that approach is the following. So consider the integer n, and then do the integer addition by 1023, and then do the bit shift operation by 52 bits. Then the resulting bits are magically uh, equal to our desired output. And this approach actually is more efficient than the left approach, and also it works for a wider range of inputs. And as we analyze the floating point implementations of math.h library, we figured out that such bit level operations are ubiquitous in those implementations. But you can see that reasoning about such mixed codes is not that easy. And this is mainly because the behavior of floating point operations are kind of continuous, but those of bit level operations are kind of discrete. So those two conflicting nature makes the reasoning of those mixed codes difficult. So that brings the first challenge that I mentioned earlier. Uh, and we partially solved this issue and presented our result at PLDI. And because of time limit, I'm not going to talk about our approach in more detail. And I'd like to move on to the next challenge, which is that the floating point, those kind of floating point implementations are usually claimed to have very low precision loss, namely less than 1 op error. So to explain what those 1 op error bound means, uh, let's consider, so let's assume that the log implementation has that much precision loss. Then it means that for any input x, the floating point output of the implementation must be one of the two closest floating point numbers to the mathematically exact result. And as you can see, this error bound is quite tight, and this claims a very strong accuracy of strong bound on the accuracy of the floating point implementation. Okay, so we now understand that 1 op error bound is a very strong claim, but then why is it difficult to prove that 1 op error bound? And to explain that, let's look at some of the results from our first paper. So this shows the op error bound that we obtained for Intel's log implementation. And you can see that our error bounds are above the 1 op error bound, 1 op error that we want to prove. But not only that, we also see that for some input ranges, the op error bound is very large, like 10 to 14. But we would like to, our goal is to prove the 1 op error bound. So there is a big discrepancy between our goal and what we proved. And some might wonder why we obtain such loose error bounds. And the main culprit of that loose error bounds is that floating point operations are in fact exact in some cases, which might quite surprise to some of you because floating point operations are usually introducing rounding errors. And those exactness happens in some special cases, like if you multiply some floating point number a by 2 to the n, where n is integer, then that operation, that floating point operation, is always exact if the mathematically exact result is not very small. And also, the similar result holds for subtraction. So if two numbers are close to each other by a factor of 2, then the floating point subtraction is actually mathematically exact to the mathematically exact result. So it does not introduce any rounding errors. And the floating point experts who implements the floating point library use this kind of exactness result to get a high accuracy implementations. But standard error analysis usually ignores such exactness results, thereby sometimes constructing imprecise abstractions of floating point computation. And this is the main reason that why we obtained such loose error bounds for some cases. So this brings the second challenge that I mentioned earlier. And we also partially solved this problem and presented it at Bopple 2 years ago. And so I'm not going to talk about our approach to solve this problem, but I will just show some of the main results from the paper. So here the y-axis represents the all-pair bound that we found, and the x-axis is input values. And those two graphs are for Intel sine and log implementations. And the blue lines show our error bounds. And you can see that our bounds are well below the one-off error bound, one-off error that we wanted to prove. Not only that, you can see that the red dots represent the actual off errors. And you can see that our error bounds are quite tight uh, in that sense. Yes, so these are the main results. And yes, right. So, but actually, we did not solve the problem fully, and we have several limitations in our approach to solve that verification problem. And to name a few, our approach still finds some loose error bounds for some cases, and in some cases, we have to do quite a lot of computation. And yeah, there are a few more, but I'd like to skip due to time limits. And yes, so this is what we did. And to summarize, we attacked the problem of verifying math.h implementations, and we encountered two main challenges in solving the problem. And we partially solved those challenges and obtained some satisfactory results for some benchmarks. And that's it. Thank you for listening.